Swayam Prabha. Digital India. Educated India.
Okay, so as I promised, this is the other lecture. Again, everything is in the context of differential geometry. Okay, and as I told you, the catchphrase of differential geometry is curvature. So you see the extent to which curves or surfaces curve. Okay, but of course, we look at curves and surfaces because we can actually see them. But curvature also makes sense in higher dimensions. For example, in Einstein's relativity theory, we have four-dimensional space, which is the three-dimensional, space coordinates, and then the fourth coordinate is a time coordinate, and there you see the curvature term actually signifies gravity, for example. Okay, so the idea is that light, when it passes across, close to a very dense star, which will have a very heavy magnetic field, gravitational field, then what will happen is that the idea is the gravitational field, of course it will have, not only gravitational fields, it will also have magnetic, electric fields, all of them. But what is important is the gravitational field is going to manifest as it's going to create a curvature in space-time, and that is what is going to make the light ray to bend. Okay, and this has been observed. Okay, so basically the catch point is curvature, and so it's far-reaching. And I've already talked to you about several things connected with curvature, and this time, as I told you, the topic is netting bondas and vadas, and it's it's getting closer to lunchtime, and it's very delicious. Okay, but anyway, this is not a cookery lesson. Okay, not that I don't like it, but I'm not a good cook. I don't know certainly to make this. Okay, but the idea is that I want to connect it to a very important theorem in differential geometry called the Gauss-Bonnet theorem. Okay, so the technical name is Gauss-Bonnet theorem. Okay, and so this is what I want to explain to you about. This is one of the most deepest classical results and goes back to Gauss, and so it has roughly about, I should say, around 300 years history. Okay, so what is this all about? So there are several aspects to it, and I will try to explain them one after the other. So let me get to to what this topic means. So you see, so you can imagine very well, you go to a restaurant and you get a plate of bondas, okay, and and you get some chutney, and then you get something, okay. But I'm not interested in that. I'm more interested in taking one of these bondas, okay, and trying to put a net around them. So what is this business of a net? So you see, what you do is that so what does that mean? So you put a net like this. So these are pieces of thread which are knotted like this, and you put a net like this. Okay, and so you do this. So this is this kind of a thing you do, and then you cover the whole thing. Okay, and basically what you have done is that you have broken it into, this is what is called a triangulation. Okay, so what you have done is you have taken the surface of the bonda, and then you have just drawn triangles on it. Actually, I really don't mind if those triangles have sides exactly straight lines. They can be curves. Okay, they can be curved. I don't mind. All right, and the curve can be of any shape. All right, and so such a thing is called a triangulation. Okay, and so you can imagine that I'm literally covering I'm netting the whole thing. Okay, so I should be careful to draw this. So the important thing is that I cannot, so this is, so what is this triangulation? Mathematically, you are covering it by triangles. And what is the rule? Any two triangles can meet at a point, or if they meet, they can meet in a side, okay? This is the rule, and you cannot have, for example, I cannot have something like this, okay? This is not allowed, okay? So this is, for example, the edge, this is one of the vertices of the sides. That vertex cannot lie in the middle of some other side, that's not allowed, okay? But of course, this is allowed, this is fine, okay? But if I remove that, this is not allowed, right? So this is what is called a triangulation. So that's what I mean by netting it, okay? And now when you do this netting, there are three kinds of there are three kinds of things that you can look at this. The three types of data. The first thing is how many vertices are there, okay? So you have, so let me show that. So you see there are these are the vertices, okay? And vertices of the individual triangles. So V is the number of vertices, okay? And then you have, so once you have the vertices, then you have the edges, okay, which are the sides of the triangles. So you have E is the number of the edges, okay? And then you have what are called as F is the number of the faces, which are basically the triangles. So you see these are edges, okay? Okay, and if I shade this whole thing, this is the face, all right? Now here is the computation that one has to do, okay? You can try it out. You calculate V minus E plus F, okay? You calculate this, and you will see this is always equal to 2. This will always be 2, okay? And it is 2, so what does this mean? So the idea is the following. The idea is, I have taken a bonda, but actually I could have taken any solid object, okay, which doesn't have a hole inside, which can be kind of continuously, made to, you think of the object, the surface of the object to be made of a rubber sheet, and then you should be able to bring it by stretching or shrinking the rubber sheet. You should be able to bring it to a spherical shape, okay? And my bonda is like a spherical shape. Okay? So basically, the idea is that you are looking at the what is called a sphere, okay? And the point is that the sphere is the same as any other solid shape which doesn't have a hole inside. So for example, you can take all regular solids, like you can take a cube, okay, or a cuboid, okay, and then of course cuboid is not regular, but you can take a cuboid also, and then you can also take a tetrahedron, okay, and then you can take there are of course dodecahedrons, icosahedrons. There are regular solids. You can take pyramids with any base, okay. Basically these are all solid shapes, and what you do in each of those cases, you are welcome to do this business. So you would take for example, take a tetrahedron like this, and then again you draw a net on it, okay. If you want if you want this to look delicious, you can think of it as a samosa if you want, okay. So what you do is you again do this business of you cover it by a triangulation like this, okay, and again do this calculation. You will always get V minus E plus F is equal to 2, okay. Now this is one kind of thing, and then I said bondas and I said vadas also. So let's go to the vada. So you see the vada is basically something like this, okay. It's a donut or a vada. Of course, I am talking about the vada, which is not like a bonda. There are also this what is called as Mysore bonda, which is literally like a bonda. Okay, I am talking about the medu vada, which has a hole inside. Okay, so this is the so-called torus. Okay, and in this case also you can do this. You can play this game. What you do is that you again make a netting of it. Okay, so you draw a net. You just draw a net like this, full of triangles. Okay, so as to cover it fully. And again you calculate this, you again calculate V minus E plus F, okay. And what is the result you will get? You will get 0, okay. You will always get 0. And if you get 0, the point is that again, it's not the smooth shape that matters. the smoothness of the shape really does not matter. You will get the same effect if you take something like this. Okay, so if I take an object which looks like a vada, which topologically looks like a vada, which means something like this. Okay, this also looks like a vada, except that it has sharp corners. Okay, even for this, if you do this business, you draw a net on it, calculate V minus E plus F, you will get 0. V minus E plus F for tetrahedron itself, directly you will see. For a cube or tetrahedron, you can directly see that V minus E plus F will be 2. You can see that. But you just have to divide quadrilaterals or polygons into triangles, and then you can very easily see that. Okay. Yeah, so that's the whole point. So I'm coming to that. So what is happening here? So you see, even for this kind of thing, which is very much similar to this, except that this is a sharp version of that. Okay, you are getting the same thing. And what you must understand is why this is very, very interesting is, see, if I start with a triangulation like this, I can make it finer. You see, what I can do is this triangulation. With this triangulation, you make any triangulation, you calculate V minus E plus F, you will get, for example, something that looks like that can be deformed to a sphere. Okay, you will always get 2. Okay, now I can further subdivide. Okay, endlessly. Okay, you do this endlessly and you still calculate, you will always get 2. In this case, you also subdivide this. You will still get 2. I mean, here you will always get 0. Okay. So what is it that's going on? So the point is that so there is a sphere, then there is a torus. All right. And what is the connection between the sphere and the torus is. This is a matter of what is called as topology. So basically, the torus is a sphere with one handle. Okay, so this, so I'll put the arrow like this. This plus one cylindrical handle. So basically, what is happening is that you are taking a sphere like this. Okay, and how do you have a cylindrical handle? You take a cylinder. Okay, then what you do is that you cut out 2 pieces, 2 holes in the sphere, and then attach it. So what you'll get is you'll get something like this. Okay, okay, and this this ball-like thing, if you shrink it, okay, then you can bring it to this shape. So a torus is actually a cylinder with one handle. Okay, and then you can think of cylinder with 2, I mean a sphere with one handle, one cylindrical handle. Torus is a sphere with one cylindrical handle. Then you can think of a sphere with 2 cylindrical handles, and that is what is called so this is called a 1 torus. Okay, and there is what is called a 2 torus, which is basically it's like sticking 2 vadas together. Basically, you take 2 tori, okay, or 2 vadas, you cut out one piece here, you cut out one piece here, and then stick the boundaries together. All right. So if you are frying vadas and the 2 vadas come very close to each other, they will stick. Okay. This is what will happen. Okay. So this is what is called a 2 torus. And what happens is that in this case, if you can, again you can do this business of netting. You can net it. Okay. And you net it. You make a triangulation. Calculate V minus E plus F. Okay. And what you will get is you will get -2. Okay. So, and you can now see what's going to happen if I take the N torus, okay, which is actually N of these guys, N vadas, or downets, whichever, depending on what you like, join to each other, 1, 2, etc. up to N. You will get V minus E plus F is equal to, so this N this N is very special. The symbol used for N is actually G, and it's called genus. Okay, so I'll just call it as G torus, small g. So it's a G torus, and this will be 2 minus 2g. This is what you'll get. So you see, in the sphere case, what happens is that there is no handle. G is actually number of handles. So in the sphere case, there is no handle. Therefore, you will get 2 minus 2 times 0, which is 2. That's what you're getting. In the case of torus, it's one handle, so G is 1. So you get 2 minus 2 times 1, which is 0. In the case of 2 torus, you get 2 minus 2 times 2, which is minus 2, right? So in general, you get 2 minus 2 times G. So what is so special? So incidentally, I must tell you that, just like the 2 torus is a sphere with 2 handles, okay, the N torus is actually a sphere with N handles. I mean, so it is G, if it's a G torus, it has G handles. Okay, and this object, if you imagine enough, this can be deformed to this. Okay, so what is happening here? So what is special about this G? This G is special in the following sense. What you must appreciate is that this G gives you, so this G is called the genus. So genus 0 is a sphere, genus 1 is the torus, genus 2 is 2 torus, and so on. This G controls this V minus E plus F. This number V minus E plus F was first discovered by Leonhard Euler. So it's called the Euler characteristic. Okay, so so I will call, so this is called as chi, which is a Greek symbol. So it's called the Euler characteristic. Okay, so this is chi. So in this case, okay, so again here also let me call this chi, and this is chi again. So the Euler characteristic is this. Okay, now so there's something going on here. Why this is going on is because purely it's a topological kind of thing that's going on. Okay, so this is what you must understand is that there is no really differential geometry here, in the sense that, see, whether you do it for a torus which looks very smooth, on which you can draw curves and talk about curvature, it also works with this thing which is not at all smooth. It has sharp edges. Okay, so it's not really the smoothness that is doing anything. There's something, it's about how this surface is covered, okay, and how many holes it has. And this is, so you must understand that this directly does not seem to have anything to do with differential geometry. That's what I want you to understand. It's a combinatorial thing. It's amazing that you do this, you create any net on this, and you calculate V minus E plus F, you are always getting this same value 2 minus 2G. And you must appreciate that even if you use any net, you will get this. Okay, you can try it for yourself. Okay, now the point is, what is going on? Certainly, this doesn't seem to have anything to do with differential geometry, right? But this part of it is what is called as topology. See, topology, the idea of topology is that two objects are topologically the same. If you think of the object, you can get one object to deform to the other continuously. And deform continuously means, you must think of the object as being made of some, stretchable stuff. Stretchable stuff you can always stretch or you can contract. You are not supposed to cut. You are not supposed to make holes, and you are not supposed to pinch. Okay, so that's the idea. So these two are topologically this way. The sphere and this box-like thing that I have drawn. Okay, they are the same, but the sphere and the torus are not the same. Okay, the cube, for example, the cube and the cube here and this guy here, they are not the same. Okay, and so this kind of study where you can continuously, if there are two objects that you can continuously deform one to the other without cutting or pasting or without pinching, they are called topologically isomorphic. Okay. And this Euler characteristic depends only on this topological notion. Okay, but the amazing thing is that this is connected with differential geometry. So that is the next part of the story that I have to come to. But I want to tell you something about the genus. So what is special about the genus? You have a question.
Sir, for the G tortoise, like for the second handle which we put, like it's when we stretch it or do something to it, two of its sides are attached to another tortoise. But like one side is attached to one tortoise and another is attached to another tortoise. But in the diagram you made, it is only attached by one side. Then how do you stretch it or do something such that it's attached on both sides?
No, say that again. What are you saying? I didn't get you. These two torus, you are talking about the two torus?
G1, sir.
G holes, yes, yes.
So for if when you do the diagram, that the second one, it is attached on it both sides, like left one and right one. But the diagram you made, like spear with handles, the rings, like when you stretch it anyway, one side is not connected to anything. So how do you stretch it in a way that both sides are connected to something?
Yeah, you see, the point is that you can so that's a good question. See, what is happening is that you can actually move the one of the edges of the cylinder, one of the circles, that can move anywhere along the surface without changing the topology. That is allowed. So you see, I can move this guy. Okay, I can move this circle along even this surface. I can move it. That I am allowed to do because it's a continuous thing that I can do it. So if you rearrange everything, you will come to this.
Okay, with rearrangement.
You are allowed to do that. So the idea is that you are allowed. You can move that. So and the important thing is whenever you make such a deformation, continuous movement, you should not make a hole, or you should not fill up a hole. You should not cut. You should not pinch. Without doing, you can rearrange. You can move it continuously. Then you will get this shape. Okay, that is what topology is all about. Okay, that's the idea. Now, what is so special about this genus? So there's a very important theorem called theorem of classification of surfaces. So if you take a surface is it's a two-dimensional thing, which has the property that it is what is called as compact, which means it is closed, okay, it is bounded, and it has no boundary. Okay, so what I mean by boundary is that if you draw a cylinder like this, okay, then this circle and then this circle, they are boundaries. So this is okay. Now if you take a sphere, there is no boundary at all. Okay, but if I cut out a disc in the sphere, then the circle, the boundary circle will become a boundary. Okay, so the moral of the story is that any closed bounded surface without boundary is, and I should also say orientable. See, so orientability is that a surface has two sides. So it should not be like a Mobius strip or a Klein bottle which has only one side. Okay, so yes, orientability means that you can have at every point you have uniformly a choice of two normals, an inward normal and outward normal. Okay, Mobius strip doesn't have an inward normal or outward normal because it doesn't have an inward and outward surface. Okay, it's all one surface actually, only one side it has. Okay, so that's called non-orientable. So you take any orientable closed bounded surface without boundary, then the theorem is a very, very deep theorem. It's not easy to prove. The theorem is that it is a sphere with n handles. Looks like a sphere with g handles attached. Okay, this is a very, very deep theorem. It's called the fundamental theorem of classification of surfaces. Right. So that is the importance of the G. All right. So basically what I'm saying is that you take any orientable closed bounded surface without boundary. Okay. Think of the boundary as it should not have an edge basically. Okay. If you take a cylinder, then there are edge circles. But if you take a torus or a sphere or a G torus, it doesn't have any edge. All right. So such a thing will always look like this, and the Euler characteristic of that means you make a net, you put a net on the triangular net on it and calculate this chi, which is V minus E plus F, you will always get 2 minus 2G, where G is the number of handles. It's called the genus. Okay, so that is the importance of the number g. Okay, so this is a topological thing. Okay, now what is so at least we would like to know what is happening here. So to understand that, we go to differential. Why do we go to differential geometry? Is because there are smooth versions. So if you take genus 0, that should be a sphere. Smooth version is a sphere. Okay, and genus 1 smooth version is a torus, and genus G smooth version is a G torus. Okay, now if you take the smooth thing, then because it is smooth, you have differential geometry. Now what does differential geometry have to offer? So I want to tell you that did I mention in my earlier lecture about spherical? I told you about spherical trigonometry, right? Did I tell you about Archimedes theorem? I don't know if you remember. So let me just say something here. So if you recall, earlier I had told you that if you take the plane, okay, and you take a triangle, okay, then you have the interior angles alpha, beta, and gamma, and you know that alpha plus beta plus gamma is pi. You know this, okay. Now if you do the same thing on the sphere, okay, and I'll take I'll take radius 1. Then what happens is that on the sphere, I just take what is called a spherical triangle, okay. And when I say spherical triangle, the sides should be, what are called as geodesics. They should be curves of shortest length. And the curves of shortest length on the sphere are arcs of great circles, the circles with, which have the center of the sphere. Okay, so you take, mind you, on the line, on the plane, the geodesics are straight lines, shortest distance between 2 points. On the sphere, geodesics are arcs of great circles, the smaller arcs of great circles. Okay, so I take what is called a spherical triangle, just like you take ordinary triangle in the plane, whose edges are all geodesics, which are straight line segments in the plane. You take a spherical triangle, it's a triangle on the sphere. The edges are now shortest distance arcs on the sphere, so they will be arcs of great circles. You take such a spherical triangle, again take the interior angles alpha, beta, and gamma. Then as the figure suggests, alpha plus beta plus gamma is greater than pi. And in fact, the difference is actually the area of the triangle. That is the amazing thing. The difference is actually the area of the triangle. And there is also what is called as hyperbolic geometry. Okay. So let me not go into that, but I want to say that you have this on the sphere. Now what I'm going to do is, let's try to understand this. See, now let us try to net the sphere. Okay, so you have a sphere now. Let us take the sphere to have unit radius. Okay, and then what happens is that I'm going to draw a net on it. So you see, I'm going to draw a net. But you see, when I draw this net, I will be very careful. I want to apply this formula. So my net should be full of spherical triangles. I just cannot choose any triangle. The sides I cannot choose at will. I will take them to be spherical triangles. Okay, and you net this sphere. Okay, and let's do this calculation. It's very, very easy. Okay, so you have, so let me call this as triangle. So this is, let us say, delta n is a triangle. This is the nth triangle, and there are, let us say, n equal to 1 to capital N triangles for the whole sphere. All right, and this delta n is the nth triangle, if you want. All right, and this nth triangle has, it has interior angles. So I will call them alpha n, beta n, gamma n. Okay, so you have so for that triangle, what happens is you have this formula: alpha n plus beta n plus gamma n minus pi is the area of delta n. Right? You have this. Now what you do is that you add all this. You add all these guys from n equal to 1 to capital N. Add all these guys. If you add all these guys, what are you going to get? See, if you add all the areas, it's going to cover the whole area of the sphere. So I'm going to get 4 pi. I'm going to get 4 pi, right? Because that is the area of the sphere is 4 pi r squared. R is 1. Okay, so I'm going to get 4 pi. And this n, there are pi of these, and how many triangles are there? There are n, so I'll get pi minus pi n, okay, pi times n, all right. And if you add all these guys, so this is where Euler characteristic will come in. See, the net has, see, the Euler characteristic will be V minus E plus F, right? And what is F? F is the number of faces, and each face is a triangle, so F is actually n, all right. And what about the how many edges will you have and how many vertices you will have? Okay, see, if you add all these angles, they are going to add up to all the angles. You look at each vertex, there are V vertices. Every angle is unique to a particular triangle and to a particular vertex. If you add everything, what should you get? For each vertex, around the vertex you are supposed to get? You are supposed to get 2 pi, right? You are supposed to get 2 pi, which is the 360 degrees. Right? Around a vertex, that's the total angle, right? So and how many vertices are there? There are V vertices. So what you will get is that if you add all these guys, you will get 2 pi into V, right? You understand this? Now, you see, the final thing that one has to look at is what about the edges? Okay. Yes. So is something bothering you? Please let me know if something is bothering you. So so you'll get 2 pi V, okay, minus pi n, okay. And what about these edges? What is the number of edges? Yeah, that's right. E will be 2n. Okay. See, because n is the number of faces, that's the number of triangles. And an edge can be common only to 2 triangles. So it's counted twice. So E is 2n. Okay. So if you plug it into chi will be, what is V? So it will be V minus E is 2n plus n. All right. But then you see, if you look at it, if you look at this calculation, you will see. So let me say the following thing. If you calculate, so I want to use this result. If you use this result, I'll get 2 pi chi is equal to 2 pi V minus 2 pi n plus pi to plus, so I think this will be, this is minus 2n plus n, let me write it, this is minus n. So here I will get minus 2 pi n. And you see here, so what I have written here, so I am supposed to get 2 pi V minus, so I want to say that I should get 2 pi chi is equal to, pardon me, there's some silly thing that I'm missing. Just hold on. So yeah, you are welcome to also look into this. It's kind of pretty easy. You are supposed to get no. So mind you, chi should be actually 2. See, chi should be 2 by whatever formula that I gave you. Chi for the sphere should be 2. So 2 pi chi should be 4. 4 pi. Okay, and that's what you are getting here. So the point is that this has to be the Euler characteristic. Okay, and let me just check that I have written it correctly. So there are n faces, so I'll get minus n. That's all right. And maybe oh, I have made a mistake here. There is some obvious thing that I am missing. What is it? Around each vertex I have 2 pi. 2 pi is angle around each vertex. So if I add all this, I am going to get 2 pi times V. That is correct. And then if I sum all these, there are n triangles, so I'll get pi n. And so something is So basically what I want to say, okay, so let me tell you what I want to say. So the idea is that if you use this formula, okay, you should be able to prove that for a sphere, the Euler characteristic is 2. I mean, the key to the proof that the Euler characteristic of a sphere is 2 is actually this formula that, if you take a spherical triangle, the excess of the sum of the interior angles over pi is actually the area of the spherical triangle. So if you have it for each triangle and then you cover the sphere by triangles and you sum up, you are supposed to get that the Euler characteristic of the sphere is actually 2 pi, it is actually 2. Okay. So what is happening here? So I want to say I want to say what is the net effect of this. So here is the, so I'm wondering where I'm going wrong. If I add all these guys, I add all these areas, I'll get the area of the sphere, that's all right. Then if I add all these guys, I'm going to get, there are n faces. N is just my f, okay. So I'll get n. And if I add all these angles, every angle accounts for only one triangle around a point, and so I should get 2 pi times vertices. That's all right. Yeah, so that's perfectly correct. So from this I should get, okay. So I'm for the moment I'm not able to think. So let me say something here. So what? Yeah, there's something silly that I'm doing here. See, every edge is common to 2 triangles. Okay. So the number of edges is, so basically what happens is that if there are n triangles, and for every triangle you count an edge, then that edge is also going to be counted in another triangle which is touching this. So the number of edges will be what? I mean,
for a triangle, there are 3 edges around it.
Fine.
2 edges are counted. 2 are counted extra.
Fine.
So total 3 and minus 2.
So how many edges should be there? It should be only, you are saying it should be only n. You are counting one, see, you are supposed to count an edge only once. All right, you are supposed to count only an edge only once.
No, so I understand. So like there are 3 n, but some lines are counted twice. So divide by
there are 3 n edges. See, every triangle has 3 edges. So there are 3 n edges, but every edge is counted twice.
3 n by 2. Then we'll get here. 3 n by 2. 3 edges will be 2 faces. So 3 n is the total number of lines encompassing the triangle, but it's counted 2 times.
Yeah.
So we'll divide by 2. So 3 n by 2. So if you put 3 n by 2, then we'll get here. All edges are counted. Total number of lines surrounding the triangle is 3 n. But every line is counted twice.
Correct.
So we'll divide by 2.
But there's a problem. Wait, no, don't be in a hurry. I mean, see, if you write 3n, okay, then the problem is that if you write 3n by 2, that's not an integer. See, if that is the number of edges must be an integer.
And it depends on n.
No, but n can very well be odd. N can very well be odd, no? So, okay, so I'll leave this to you. For the moment, let me say the following thing. Let me say the following thing. Somebody has to want to say something? Darwin, you? No, I'm just.
N can very well be always even.
N can.
Applying the logic such that n.
No, see, sometimes you start with an n given a geometry situation. Then it happens that n turns out to be, it may turn out at the end to be, n can only take an integer value. which is even, for example, or odd, that kind of thing can happen. See, that is because of the geometry or topology. But what I want to say is that, see, anyway, let me come back to the following thing. Somebody raised the hand. Was it Davin? You want to say something? Yes?
N can't be odd.
N cannot be odd. N cannot be odd, you want to say. That's all right. Okay. That's okay. But that is, I mean, you can't assume that. I mean, you have to prove it. That's okay.
So, fundamental logic is logic. That's what I'm saying.
That's okay. I agree. That's right. But then you get the formula. That's what you want to say. That's all right.
Everything is number. It's counted twice. Does not have a plot. Then we have plot, then we have to consider and be plot or not.
That's right. Okay. That is more or less okay. I agree with that. Okay. But I want to say the following thing. You take a surface. So let me say what we have got. You take a surface of genus G greater than or equal to 0. Okay. So here is the statement. The statement is, if you calculate, so here, so in this case, let me write this down. I am getting 4 pi is equal to 2 pi times chi, that is 2 pi times v minus e plus f. This is what I am getting. Okay. See, basically chi is 2. Okay. This is for the sphere. Okay, this is what I am getting. Okay. You fix that, it's not a big deal. All right. Now you get this. I am just saying that you will get it just if you use this simple formula that the sum of the x's or sum of 3 angles of a spherical triangle over pi is actually the area of the triangle. Then you fill the whole thing with triangles, and then you get the total area. Use the fact that total area of the sphere is 4 pi. Okay, you do this. Now, what is going on? So where is the differential geometry part coming here? What is this 4 pi? See, if you think about this 4 pi is actually, so I will tell you something. The sphere has what is called as curvature plus 1. So this is what is called as Gaussian curvature. The sphere has what is called as Gaussian curvature plus 1. Okay, and this 4 pi is the area. So this 4 pi can also be written as integrate over the sphere, okay, over the area of the sphere, the curvature function. Okay, see, what I want you to understand is that if you take a surface, at every point, if S is a surface and P is a point of the surface, at that point there is something that is called the Gaussian curvature. Okay. Okay. Now what you do is that you take this Gaussian curvature function and then you integrate over the surface. That is the total. This is the total curvature. Okay. In the case of the sphere, this k is 1. Okay, so this will become integral over the sphere 1 dA, but integrating dA will give you just A, and that is the area of the sphere, so you get 2